Will it work or will it not? That is the question, and it is. So, yes, I am recording this. Okay, so example 2B from continuing on from yesterday. All right? All right, so here we have, it says, how long would it take for $10,000 to grow to $15,000 if it is in a savings account that pays 2.59% interest compounded continuously? So remember, we are using the form A equals P E R T. Okay? So what is our future value? 15,000. So we're going to put that on underneath the A. And 10,000 is our current value. And it'll be E to the what? 0.0259 T. Okay? So, we need to get E by itself. What do I need to do? Okay, so we're going to divide both sides by 10,000. And when we do that, we have 1.5 equals E to the 0.0259 T. Now what? What type of log? It's a special kind. Natural log, yes. We're going to take the ln of 1.5 and the ln of E to the 0.0259 T. Okay, so what happens to our exponent, Gunnar? What happens to our exponent?
It goes to the front of the natural log.
Yep, it goes to the front of this, right? So this all just kind of goes bloop right there. Okay? So now we have natural log of 1.5 equals 0.0259 T natural log E. Now what do you guys suggest?
Get the natural log of E, which is 1.
Yep, so you guys, exactly. Let me change my color here. This all goes to 1.
Let's just cancel out.
So 1 times 0.0259 T becomes just 0.0259 T. Okay, so now what else can we do? Divide them both by
0.02.
Yeah. Yeah, we can do that. You can do both. You can do them both at the same time, actually, right? So if you use your calculator and do natural log of 1.5 divided by 0.25, T should be, I got 15.66 years. Okay, you guys might want to check my work there to make sure. Okay. So when a substance has a half-life, T half, a formula for the amount of that substance that's left after time T is the following. And this is how it's derived. It's kind of confusing. So remember, we talked about half-lives last semester, I think it was, wasn't it? So A over 1/2 is the same as A to the B to the T of the half-life. Okay? So A is your beginning amount, right? That's an A over 2. So A over 2. So A is your beginning amount, right? Oops. Okay, I didn't spell that very good. So A is your beginning amount. So we're trying to find out when it is half that amount. So that's why we're dividing by 2.
What's B?
Okay, B is the ratio that you're using. Okay, T is the time when it is half-life. Okay? So, we want to know when it is exactly.
Wait, so is that the equation right there?
So far, we're going to derive it. I'm going to give you the final equation in just a minute. Okay? So, on both sides we have an A. What can I do about those A's? Divide them both by A and then they go away. So I'm left with 1/2 equals B to the T half. That make sense?
I don't get the T half.
Well,
It's time when it's half the amount.
Why would you write half?
So when does this be T?
No, because it's a specific T.
Can't you
We-
just do 0.5? Why don't we do like H then?
Oh, yeah, isn't that point?
Okay, TH would be fine. You
No,
could do
like
that.
just H. It just doesn't make sense.
All right.
Wait, is that the same as...
Okay, so we have this so far. That is the same thing as saying if I were to solve for b, I could say that is 1/2 to the 1 over t half equals b if I'm solving for b. So think of it this way. If I have 1/2 to the b to the 2, how would I solve for b in that case? Yeah, 1/2 to the 1/2, right? If I had to get b by itself. So I'm doing the same thing, but it's still in a variable. I'm taking 1 over that variable
Why?
because I need to get b by itself.
How does that help?
I'm solving for b, so I needed to get rid of this exponent. So, okay, so now we're going to put this together with something that we've had before, and that is y equals a to the bt. That's what we started off with originally, okay? We're going to replace our b with this. So now it is officially going to be y equals a times 1/2, and it's t right here, so t on top of t half. So this is the formula that you're going to use to find our next problem.
T over T half?
Yep, t over t half, and I am recording this. Yes.
So total years for it to be all the way gone over total years for it to be half gone?
Yep.
Okay.
All right. So carbon 14 has a half-life of 5,730 years. Okay? From this assumption, find the approximate age of a skull found by archaeologists that has 67% of its original. Okay? So I know that I have 0.67 of the original. That is going to be equal to, and I'm going to keep my a here, because I'm going to use this formula. So a times 1/2 to the t, and what's my half-life? 5730.
Is that a 1 for the one that's boxed in? Is that a 1 over t to the half?
That is a t over t to the half.
Wait, why'd you get the 1.67
Because of
67% 67% right here of its original.
Oh, of the original.
Yep. So if I divide both sides by a, the a is canceled. So I'm left with 0.67 equals 1/2 to the t 5730. Okay? We are trying to find the original age of the skull. How long has it been around? Okay? Not yet. We have something to an exponent. So what am I going to do?
We need to raise both sides to 5,730.
Or I can take the log of both sides. Log of 6.67 equals log of 1/2 to the t to the t over 5730. Okay, what happens to my exponent? It moves to the front. Okay? So now I have log 0.67 equals t over 5730 of log of 1/2. How do I get rid of my log of 1/2? Divide both sides. Okay, so I'm going to go up to here now because I'm running out of room. This will be log of 0.67 divided by log of 1/2 equals t over 5730. Okay, now how do I get t by itself? Multiply both sides by 5730. So 5730 times the log of 0.67 over the log of 0.5 is the same as 1/2, right? Equals t. So if you put that in your calculator, you'll find that t is going to be around 3,310 years old, 0.6. Okay, so the skull is about 3,310 years old.
Oh man.
All right, so we're going to do the same thing. This time we have potassium 40 decays to argon 40 with a half-life of 1.5 billion years. So making this decay suitable for dating the oldest rocks on Earth. If 35% of the potassium found in a rock has decayed to argon, how old is a rock? Okay, if there's 35% left, how much has already decayed? Yes. So we needed to change that to 0.65, you guys. Because before what we had was how much had gone, okay? So this is going to be 0.65A.
And 0.65 has deteriorated.
Yeah, 65% has deteriorated. Equals A times 1/2 to the T over, and here's the thing, 1.5 billion. That's a lot of zeros. I'm going to just say 1.5b until we get further along, and then we have to change it back to zeros, okay?
Yep.
All right, so now my a's cancel. You remember that. What would be the next step?
The exponent goes to the
So log. Yep, so we can do a couple steps here. We know that we have a log of 1/2, and I think one of you guys said to go ahead and put this in front of that. So it'd be t over 1.5 billion. Okay, so we did a couple steps in one. All right, now, how do I get my t alone?
Divide by 0.5.
Yeah, divide by log of 1/2. So log of 0.65 divided by log of 1/2 equals t over 1.5 billion. Okay, at this point, before we go any further, we should go ahead and put this in our calculator and then switch this to our billions. We need to put that with all the zeros in it. Okay, we use the B for shorthand, but we need to change it to billions.
Did we get
Question.
Yeah.
0.62?
Where'd you get 0.65 from 35%?
Okay, so 35% is left. How much
Oh,
deteriorated?
got it.
Okay, so here, this would be now,
Would it be 0.62?
it might be, I didn't actually figure it out. 0.6215, is that what you got?
Well, how many do we need?
So log of 0.65 divided by log of 1/2. Is that what you guys got? Okay, so that is all over t of 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. 5, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you could. Okay, if I multiplied this times this,
1.5. Yeah.
yep, okay, this will be 930 and 6 zeros after that.
6 zeros?
So about 930 million.
Equals T,
Yep,
which is a 4 times.
yep. So the rocks are about 930 million years old according to this.
Wait.
No, that's after it's decayed for
Wait, I
65%
got
of it.
9, 3,
No, this is how old the rock is.
0, 0, 0. You would just
Oh,
do point.
Okay, so now I want to give you guys a formula. If you have a base in like you're working with base 2 versus base 5, how do you convert it to be the same base? Okay, so if you have a log in one base and you want it to be the same as a log in another base, how do you convert that? So this is one way of writing it. This is a formula. Log base B of A equals log base B of C times of A and log C of B. Okay? So we have something in log base B. It's the value is A. We want to convert it to log base c instead. So I'm going to take the log base c of that value a and divide it by log base c of the base b.
What if you want to make it the same as another one? So you have log base b of a and log base c or whatever, and you want to make the b1 c.
Yep, we're going to do something like that in just a second here. All right, so the change of base theorem is helpful for calculators that have only a common logarithm key or a natural logarithm key. So in other words, in base 10, you want to switch something maybe to base 10, and you're working with base 5. You want to get it to base 10 so that you can put it in your calculator. Okay? So like this one says evaluate log base 5 of 71 to the nearest millionth. Well, if you have a regular calculator, you won't be able to do that. It needs to be in base 10. So let's switch this to log base 10. Okay? So to do that, I'm going to say log base 10, and I'm going to have the a value, which is what in this case? 71. Over log base 10 of the b value. What's our b value? 5. So when I find that, it's going to be 2.648. Okay? And I didn't take it out to the nearest millionth. I just did it.
Would it be 4 9? So that was 5.
Round it up? Yep, it could be. Okay. So now do the same thing for example 4b and see if you can do it. Okay? So we're going to switch this to log base 10. We have log base 10. What's the top part going to be?
600.
600. Good. The bottom is going to be,
2.574. Done.
okay. Good. You guys got it. That's it. Finito.